Welcome to the Silicon Design and Verification Intelligence demo, built on the IntelligenceIQ framework. In the next few minutes, I'll show how we navigate from identified events to trends to intelligence, while incorporating a learning loop. This demo focuses on defect prediction in silicon design and verification, spotting high-risk issues early, so they never escape the silicon. We'll use 3 representative challenge areas: timing closure degradation, power anomalies in voltage islands, and DFT coverage gaps to show how IntelligenceIQ detects, prioritizes, and resolves them end-to-end. First, we start on the dashboard. At the top, the command tiles summarize the health of the tape-out. Total risk exposure by domain, violation density versus design complexity, mean time to resolution, number of active events detected, and the design velocity trends. Together, they tell us whether we're converging fast enough and where guardrails are being breached. To the right of the dashboard, trend widgets show how critical events per build, violating paths, and blocks above guardrails are behaving over the last few weeks. This gives leaders a one-page view of exposure across timing, power, and DFT. Just below, the critical events panel lists our 3 key events. Each card shows when it was detected, which block it affects the impact and AI confidence. For example, timing closure degradation, clock domain 3, is flagged as critical, with worst slack at minus 250 PS, over 1,200 affected paths, and 94% confidence that this is a real risk to tape out. From here, the engineer can click any event. Let's start with timing closure degradation, to move into Trend IQ. Trend IQ is where IntelligenceIQ does deep pattern detection and correlation. At the top of the screen, you see an event filter ribbon listing all active trends: timing closure degradation, power anomaly, DFT coverage gap, and so on. By default, we're focused on timing closure degradation issue. On the top, the trend analysis chart shows setup slack degrading over the last 18 hours across more than 1,000 paths. You can see the curve bending down as new RTL drops increased combinational depth. Below that, a correlation matrix ranks the key drivers: logic depth, clock tree imbalance, wire load and temperature drift, and the ML model used to detect them. Each row shows correlation and the current status. For the other events, the same layout works. For power anomaly voltage island 2, Trend IQ shows peak power spikes tied to clock tree imbalance, toggle rate increase, island load skew, and local thermal hotspots. For DFT coverage gap emerging, it highlights coverage dropping after RTL logic changes, the number of untestable nodes, and which modules are contributing most of the gap. Once the engineer understands why the trend is happening, they step into Decision IQ to choose the best fix. Decision IQ acts as a control tower for each event, orchestrating the decision lifecycle and managing AI confidence. Across the top, you'll notice the same event slicer, so we can flip between timing, power, and DFT decisions without leaving the screen. For timing closure degradation, the AI case analysis card tells us: AI confidence, 94% primary recommendation. Insert a pipeline stage between register banks in clock domain 3 at expected timing gain, plus 320 PS of slack, resolving about 89% of critical paths. A compact impact assessment section quantifies: area impact, about 0.08% gate count increase, power impact, plus 0.4% total, estimated verification effort, 2 to 3 days, thanks to existing regression suites, predicted risk to schedule if we do nothing. Below, a similar historical cases strip shows 3 past timing incidents, the fixes applied, and their outcomes. So the engineer can see that pipelining has historically driven over 90% success on similar patterns. Every Decision IQ card also includes an alternative strategy. For example, derating the clock by 5%, with lower implementation risk, but visible performance penalty. The decision owner can compare options side by side before committing. For power anomaly and DFT coverage gap, Decision IQ applies the same pattern: AI recommended actions, quantified impacts on power, coverage, and rework, and links to prior cases in memory. Once a path is selected, Decision IQ sends into Action IQ as a structured execution plan. Action IQ turns a chosen decision into tasks, owners, and timelines, then tracks progress and outcomes. For each event, we surface 4 tight subtabs. Overview shows the implementation SLA, numbered tasks completed, days to tape out, and AI confidence on the chosen fix. A brief issue description and business context explain why this work matters, whether avoiding a res bin, power budget breach, or test escape. Tasks breaks the work into an 8D style checklist. Root cause analysis, RTL change, synthesis and PNR reruns, regression, and sign-off. Each task has owners, due dates, and progress bars, so program managers can see exactly where execution stands. Timeline visualizes key milestones as a vertical activity stream. Decision created, owner assigned, design change merged, regressions passing, making audit and communication effortless. Team and comment highlight the cross-functional squad working on the issue and the discussion thread, keeping architecture, design verification, and DFT aligned in a single workspace. Every status update and outcome here is fed back into the learning repository, ready to improve future detections and recommendations. Finally, Effectiveness IQ shows a before versus after story for each event. For timing, we compare baseline versus current. Cycle time to close timing reduced from X days to Y days, violating paths cut by Z%. First pass success probability stepping up. Similar tiles quantify the impact of the power and DFT fixes on energy, coverage, and rework, plus an overall design velocity and yield uplift, directly tied back to the Intelligence IQ loop. Together, Trend IQ, Decision IQ, Action IQ, and Effectiveness IQ transform silicon design from reactive firefighting into a continuous learning system, detecting risk early, choosing smarter fixes, executing with discipline, and proving measurable improvement every tape out. And that concludes the demo.